a little tricky. Let me see, I might have an easier one here that I could do first. Okay, I'll start with this one. So we have a triangle with in center I. Whoops. And O is the circumcenter, and D is a point on BC. Okay, so D is any point on BC, and then we draw the circumcircles of BID and CID. So we want to see where BID cuts AB, and then we want to see where CID cuts AC. This is kind of interesting. I've never kind of seen this kind of configuration before. So maybe it could look a little bit like that. So actually, I can make both these circles kind of, yeah, I can make it more like this. I think that would be fine. So kind of a little more symmetric. So this right here is E, and this is F. And then we draw the circumcircle DEF, and we see where it cuts AB and AC. Okay, so this would be M and N up here. Let me see if I can make this look a little nicer. I think it's always going to cut it kind of close. Maybe something like that. So this is M and this is N. Let me close this. I could also move point D around. Like that. So this is M, and this is N.
I have seen this problem before.
Oh, really?
But this wasn't from the Saudi Arabia. I mean, it probably was, but I saw this in the first part of problem in Junior Bulk Math Olympiad shortlist.
Oh, really?
And I saw before someone on some Discord server asking about the second part of the problem also.
Because it's like a two-part problem.
Yeah.
But was the first part like in the Balkan? Was it junior Balkan or normal Balkan?
The junior one. Okay. I think the first part is not hard at all. Don't know about the second one.
Okay. Let's see. So this is P and this is Q.
I think that you mislabeled point F, because F is the intersection of CID and segment.
Oh,
AC.
Yeah, you're right. So F should really be, I don't want it to be on the circle. There we go. But now it looks like O and I are too close. So let me
just hide the in circle.
Yeah, I think you're right. Okay, so eventually we're gonna, so that's P. This is Q. And then there we go. So M and N, I think I could draw. Okay, one's gonna, I think they're always gonna be on different sides of E and F, right? So
about this problem, now I found it was shortlisted 2019. It was G6, and it was proposed by Saudi Arabia, so it makes sense.
okay, so they did propose it at least. Because yeah, I know they've taken some problems from Vietnam before, but at least they proposed this one.
They just reused it in their competition.
Yeah, they just reused it. So EN, FM, and PQ. This is interesting because this is like a very general configuration, I feel like. And then we want to show the median of vertex I bisects arc BAC. So yeah, this is like a very general configuration. So I feel like it could probably be useful in a lot of problems. Okay. So it kind of feels like it might use some stuff with some medians because we want to show yeah, what if we draw the circumcircle of IPQ? Yeah, it looks like IPQD is cyclic, and that's probably an angle chase. Let's think about that.
I've solved the second part. It isn't actually hard.
Oh, really? Okay.
I think I is the incenter. I mean the circumcircle of the circumcenter.
Oh, is I the center of this circle? DEF?
Yeah.
Interesting. And then once we know that, so yeah, we know EMF N is cyclic, and so we kind of have to show it's an isosceles trapezoid, right? But angle MEN is, let's see. So angle AMF is angle EDF, and angle AFM is, are they both EDF? Wait. No, AFM so yeah, we want to show MDE is FDN.
So I think that proves that EN is parallel to MF is easier than. Let me show the solution. Okay.
Okay.
We have AE, I, and F for cyclic, right?
Right, by Michel's theorem.
And AM, I, and N too.
Is that also,
Yes.
let's see, by Michel's theorem?
Yes. By Michel, and so that we have triangle IME is similar to triangle INF, and because IM is equal to IN and IE is equal to IF. So that triangle IME is equal to triangle INF. So that AM is equal to FN.
Okay. So yeah, so that shows that ME is equal to FN, and so then we know that MF is parallel to EN, right? All right. And then for PQ,
I think it's just Reims theorem. You know about Reims theorem?
yeah, so basically by Reims theorem, we have PQ is parallel to both EF, EN, and MF, basically.
No, I think by Reims theorem we have EF is parallel. Wait, wait. I don't think it is. I don't think it's Reims theorem. I think I made a mistake
Okay.
because
The
by Reims theorem it must be a different line, not that line. Yeah, I'm mistaken.
Oh, no, sorry.
actually, you can use Reims theorem if you prove that HQ and HZ is a polynomial.
Yeah, we have to show.
That's right.
So this almost looks like they're tangent. So yeah, we want to show HQN or HPM are collinear. It almost looks like it's tangent. I don't know if that's just a coincidence. Yeah, it's not tangent, I don't think. Okay. So yeah, can we show those are collinear?
I think it's a similar that what I have proved that so we have ND is parallel to FH, which we can say that F and H and ND is reflection over CI, so that we have N2H constantly by the reflection.
Oh, NQ and H are collinear?
Yes.
So sorry. So how did you do that?
Similar what I have proved before, so that we will have N is the reflection of D over CI, F is the reflection of H over CI, and SQE are concentric, so that NQH are concentric.
Okay, so H and E are reflections over BI, and D and F are reflections over CI. That's what you're saying, or D and N?
Yes.
Hold on. So basically, if I reflect D over, yeah, and then if I reflect H over CI, I would get F. Yeah. So so that's why H, Q, and N have to be collinear, because basically angle HQD, we want to show it's the same as angle FQN. Yeah, because it's just symmetry, because since FQ and D are collinear, then and everything's just a reflection, then yeah, HQ and N have to be collinear. Okay. And then we could use Reims theorem, so we could show PQ is parallel to the two of them. Part B is easier. How do you do part B?
Like it's almost trivial to me because we can see that BPQC is cyclic, right? Because IP times IB is equal to ID square.
Yeah. Okay.
Okay, so IG is the median of IPQ, right? And
Mhm.
so it will be the median of IBC because of the, because they are both
Yeah.
similar. So we have IG is the median of IBC. However, if you label the mid arc of BAC, let's call it point X, then IX is also the median.
That's like a
So
well-known fact because if you take like the circumcircle of this and then you like draw the
yeah, the
two
tangents.
yeah, they'd have to concur, yeah, at the midpoint of that arc. All right, so I think we've got
Arc
this.
is even easier.
Yeah. All right, so
That will be
let's.
same as my solution for the second part.
Okay, that was the same idea that you had.
I only angle traced the cyclic quadrilateral instead of doing a PowerPoint, but it is okay either way.
Yeah. So yeah, you angle chased it instead of using PowerPoint. All right, so I'm just gonna. Okay, so let's do this step by step. So first, we need to show that IPQD is cyclic. So let's see. Is it so IPQD? Yeah. So let's do it like this. So yeah. So step one, I'm going to show IPQD is cyclic. So angle PDQ is PDI plus QDI, which is yeah, so it's kind of easy, but angle PDQ is angle PDI plus QDI, which is angle EDI plus angle FDI, which is angle EBI plus angle FCI. And then that's easy to show. Yeah, that's 180 minus BIC. So that means DPIQ is cyclic. Let me see if this helps. And then, so let the circumcircle DPIQ meet BC at H. And then, so then we want to show that DE, we want to show that all these points lie on a circle. So we draw the circumcircle D. We want to show that H lies on that circle, right? But that's probably okay. So first, it's not hard to show that IEM is congruent to IFN. So IE So yeah, so first I'm going to say AMIN is cyclic by Mikkel's. Well, first of all, we know AEIF is cyclic by Mikkel's theorem. So and so that means that IE equals IF. Since AI bisects angle EAF. And then we also have IM is equal to IN, but to do that, we have to show that BMIH is cyclic. So
Do we need point H at all?
maybe not. Like I thought we used point H to, like, we proved that to prove that PQ is parallel to EN because basically we showed angle HQP is I thought we showed HQP is HDE is HNE, so I thought that's how we showed like EN is parallel to PQ, but I'm not sure. Maybe we don't need H. And then I also thought we showed like MNIH is cyclic, so like that meant that by Mikkel's theorem AMIN is cyclic. But so showing AMIN is cyclic. Yeah, I'm not sure what we need.
For proving EN is parallel to MF, it is enough just to show that I is the center of that circle, right?
Yeah.
Because of the angle bisector symmetry. And that is not hard to show since AI is equal to AF, ID is equal to IF because of the angle bisector, and similarly ID is equal to IE.
Okay. So ID is equal to IF because oh yeah, okay. So all right. So yeah, we might not even need that AEIF is cyclic. So we have ID equals IF. I'm actually going to delete this. Well, I'll just leave it there for now. But basically, we have ID equals IF since CI bisects angle DCF. It's like the same idea. So similarly, ID equals IE. So I is the center of the circle DEF. So yeah, so then we wouldn't need point H. Don't think. Okay, so well that would help prove EN is parallel to FM. But for
I have an angle trace for the PQ part. So basically DPQ is equal to DIQ, which is DIC that is equal to DFC, and that is equal to DFN. Did you follow?
Yeah, yeah.
And
Oh,
that
no,
is equal to DN.
That's a nice one. Okay, so I'm just going to get rid of point H. We could just do it that way. So dpq is diq. dpq is diq, which is dic, which is, I think it's, is it dfc? Yeah, dfc, dfn. Then DFN is DEN. It's a nice one. Okay, so so PQ is parallel to EN, and similarly FM. All right, and then once we know that, then we can do the stuff with symmedians. So I'll just say let G be the midpoint of PQ. To make things easier to mention later. I'll say NJ be the midpoint of arc BAC. So, so first we have BPQC is cyclic. And that we could just find that using angles, because angle IPQ is IDQ, which is IDF, which is I. Yeah, so yeah, I'm just going to do the angle chase instead of the power of a point. So angle IPQ is angle IDQ, which is angle IDF. I think that's F, right? Yeah, which is ICF, which is angle ICD. And so that means that BPQC is cyclic. I see we have Akan joining us. Hey Akan, thanks for joining us. So this is this our fourth problem? I think this is our fourth problem. So the first one we didn't solve. It was tricky, but I think we're pretty close, but the rest of them we've solved so far. So once we know BPQC is cyclic, then IG is a symmedian of IPQ. Since IP is a median of IPQ, it's a symmedian of IBC. So it's a symmedian of IBC. And then once we know that, so then that means that IG passes through the tangents at B and C to, I'll say IG is concurrent with the tangents to the circle IBC at B and C. So that means that IG passes through J because those concur at J. That's not hard to prove. So IG passes through J. That implies that the I median of triangle IPQ bisects arc BAC. All right, that was a fun solution. And yeah, we solved it pretty fast, I feel like. Yeah, we didn't need that point H. So I will move on to the next problem. Oh, this is only our third actually. Okay, so let's check this one out. So we have a triangle ABC with in center I. Let's draw the circumcircle and the in center. Do we ever use the in circle? I'm not sure, so I'm just going to draw angle bisectors for now. So we have this, and they meet at the midpoints of the arcs. So, oh, whoops, I'm going to want to make this A, and this B, and that C. So this is D and E. D is the midpoint of, those are the midpoints of those arcs. I is the end center. DE cuts, okay, so we want to see where DE cuts AC and BC. It does it at F and G. Is AF? I don't think CFG is isosceles, is it? Oh, maybe it is. It is. Okay. So let P be a point such that PF is parallel to AB. All right. And then we want PG is parallel to BE. Oops. So it's like kind of like we would have a parallelogram if we extended a few things. Okay, so this is P. And then suppose the tangent lines at A and B meet at K. So maybe we'll use some medians here. And we want to show that AE, BD, and KP are concurrent or parallel. All right. So yeah, we can't see point K. So let me shrink a couple things. Just want to see that point K. All right, so that looks good. Maybe I'll move it down just a tiny bit. Make it look nicer. So here we have a point K. PF and PG. All right.
Actually, by using Pascal theorem, we need to prove that K, I, and B are linear. So you don't need to draw line A, E, and B.
AE and BD. Oh yeah, yeah. It's going to be hard to draw this, but
I mean that you don't need to draw that line because by using Pascal theorem, we need to prove that K, I, T are collinear.
Ki and P are collinear. Okay. So once we show Ki and P are collinear, then that would solve it, is what you're saying? Is that Desargues' theorem?
I think it can be proven with Pascal's theorem,
Okay.
but there are other ways to prove it, like polars and stuff like that. I think the
Okay.
Pascal's is the shortest.
So since if Ki and P are collinear, then that means, well, so basically we're saying that AE, BD, and IK are concurrent. Is that like a well-known fact?
Yeah.
Okay. I wonder if, so yeah, you said you can prove it with Pascal's theorem, right? So I wonder, yeah, basically we want to show K lies on the radical axis of those two circles, right? We know that Ka equals
I think I can prove that K lies on the radical axis.
of those two circles.
Yeah, I have seen this configuration before, and K does lie on the radical axis.
Okay. How do you prove it?
Yeah, you can just label the intersection of Ka with the circle. Yeah, that circle right there. And similarly, and if we can prove that HA equals JB, then we're done.
Yeah.
Yeah, and I can prove it. Just wait me a second. I wrote this problem down, I think, and I need to check for a second.
Okay. It almost looks like HI and J are collinear. Yeah, that does look true. It looks like HI and J are collinear. If that's true, yeah, that would solve it if that's true. So maybe that's just like an angle chase showing HI and J are collinear.
Well, we can prove AH equals BJ by using congruent triangles.
Okay.
Yeah.
I think actually everything can be angle traced here. Instead apart from the Pascal's and.
So because AHI is AEI, which is AEB, which is KAB. So yeah, that solves it pretty much. Yeah.
I actually didn't think of those points, but if you introduce the other intersection point of those two circles, then FPGL is cyclic, and also ALBK. And those two both can be angle traced, I think. And after that, I think it is just some more angle tracing. So to prove that those 4 points are clear.
Okay.
So but either way works. So
okay, so let's start. So did you prove that K lies on the radical axis of these two circles yet?
It would be proven if we show that those 4 are collinear.
So like the first step is showing that. I guess I'm just thinking about the order we want to prove things in. So like to show that they're concurrent, that's the same as showing that K lies on the radical axis of these two circles, right? Which is the same as
yeah.
saying that P, well,
We only need to prove that those four are collinear.
yeah, we have to show that these four are collinear, right?
Can you check if PFH is collinear?
Yeah. Yeah, it looks like it. So yeah, maybe that makes it a pretty easy problem.
Yeah, so basically I can prove that K lies on the radical axis. So we just only need to care about P.
All right.
Yeah, so I'm finding a way to prove that those two are collinear.
I think I can prove that P is on the radical axis. So combining that, we should be okay.
All right. So first I'm gonna show that K lies on the radical axis. So I'll just start out by saying consider the circles AEF and BGD. All right. So first, how do you show that K lies on the radical axis of those?
So I'll prove it. Okay. Can you call the intersection of HE and circle ABC?
Okay. So that point.
Yeah, and can you just label that one? And I will prove that DM is parallel to AB.
Oh, but aren't we first going to show that K lies on the radical axis of them?
Yeah. I'm proving it. I'm using it. I need this property first. So
Okay.
since HA is the tangent, so we have wait. Let me do a little bit angle trace. Can you just wait a second?
Okay. But so HIA is HEA, which is CBA. I think.
Oh yeah. So we have HA is tangent to the circle, so we have angle HAD is equal to HAD is equal to the ABD.
Okay.
And we also have that HAD is equal to HAI, which is equal to MEB. So we have MEB equals DBA. So it must show that MD is parallel to AD.
Parallel to AE.
To AB. MD is parallel to AB.
Okay. All right. So hold on one second. I think it's like our Okay, sorry, let me read what Nguyen said. So hold on just a second. So first, so did we even prove that AIFE is cyclic? So I think that might just be obvious, but did we prove it?
Yeah, it is because FEI is equal to FAI.
Yeah, okay. So I'm going to start out just writing that. So angle FEI is equal to angle DEB. Angle DAB, which is angle FAI. And so that implies that FEAI is cyclic. The DGIB is cyclic. Okay, so first I'm going to write out what Nguyen said. So he's saying K lies on the radical axis if and only if KL and I are collinear. So we have ALI is equal to AFI. Okay, so LI is angle bisector of ALB. Sorry. Okay, I think your way works with the point M. I just want to read Nguyen's solution because I think it might be a little faster. Okay, yeah, I think, yeah, I think Nguyen has a pretty fast solution. So I'm just going to write out how Nguyen did it. But yeah, I think your way works too. It's Khan. It's just a slightly longer. So all right, so let me write that out. See how this looks? Okay, that looks good. And then since Ka equals Kb, that means that Li and K are collinear. That's a nice way to show that they're collinear. So actually, let me define L. And actually, do I even need to show that FEAI is? Yeah, I think I want. Yeah, I want to show that that's cyclic. So I'll say, let those circles intersect at I and L. Okay. All right, I'm just going to delete this for now. I think it would have worked, but I think this is good enough. So, and then, so then we can use an angle chase to show that PFGL is cyclic. Because
and then
angle
chase that P, L, and I are collinear after that.
Okay, so first I'm going to do the angle chase to show that PFGL is cyclic. So angle FPG is angle EID. And then that is basically 180 minus this minus this. But yeah, how do we find that there might be an even easier way than I'm thinking. Hold on just a second. So,
We can calculate FLG.
We can calculate FLG as 360 minus FLI minus GLI, right?
Yeah.
Which, so yeah, I think that's a good way to start writing it. So angle FLG is 360 minus angle FLI minus angle GLI. And then that's the same as angle FAI plus angle GBI. And then once we know that, it's not hard to see that that is equal to 180 minus angle AIB. So let me just split this into two lines. Which is 180 minus angle FPG. So that means that FPGL is cyclic. And then once we know that, we can use an angle chase to show that PL and I are collinear. Because angle PLG, we could try to show angle PLG is equal to angle GBI, because PLG is PFG, which is IDE. Yeah, so is that right? PLG is PFG, which is IDE. Which is IDG. So that basically shows that PL and I are collinear. So, and then by the radical axis theorem, PAE, KP, and BD concur or are parallel. All right. So I'll move on to the next one. So yeah, this is really just a lot of angle chasing. There's no, I feel like there was nothing like really sort of amazing in this solution, but it's just, yeah, a lot of angle chasing. So this one is from the Iranian Geometry Olympiad this year. So let's see if we can solve it.
Sorry, I have tried that one time, and I think it's absolutely hard. It's absolutely hard. So we don't
Oh, this is really
have to
hard.
solve it.
I remember the solution is only using angle, but it's the hardest one.
Okay.
Like there was 5 problems. One of them was combinatoric geometry, and
Okay.
I didn't do the combinatoric one and this one.
Was this one easier?
No, this is the 5th problem, which is the hardest one of IGO.
This one right here, or the other one?
Yeah, this one is the one of these. I think the second hardest.
Okay. So these two are both pretty hard, basically. Do you guys want to go back to the first problem?
Can you just there's 2 easy IGO one.
Okay.
No, this one is the hard one. The Euler line is the hard one.
But is this one easier?
Yeah, this one easier.
Okay. I'll do this one. Just a second. So we have a triangle. We draw the altitudes A, B, B, E, and CF. Yeah, I wish there was a way to do altitudes. So this is D, E, F, G, and H. The perpendicular from H to EF, we want to see where it intersects EF, AB, and AC. So I'm going to have to probably extend a couple things. So we have it does it at P, T, and L. Okay. That's P, this is T, and this is L. And K lies on BC such that BD equals KC. So what I'm going to do, let me see. So this is point K. Then we have a circle that passes through H and P and is tangent to AH. Let's see how I want to draw that. So I'm going to draw the perpendicular bisector of PH and see. Okay, so it would be this circle right here. Okay. And we want to show that the circumcircle of ATL and that are tangent. And that KH passes through the tangency point. That's interesting. All right, let me check the chat. Okay, your solution is a little long. Let's see if we can come up with a quicker one then. Okay, so G is the center of it. Let me try to draw the best picture I can.
The tangency point lies on the circle of AEHF.
Oh, interesting. All right. That is good to know. So it
I
lies
don't know
on,
the proof, just saw it.
you just saw it, you saw it with GeoGebra. All right. So yeah, somehow, so maybe it's better to do it that maybe we should just let these circles intersect. And then we could show that IPH is the circumcircle of IPH is tangent to AB. Wonder if that's the best way to do it then. So to do that, how do we show the circumcircle of IPH is tangent to AB? Basically, we want to show angle PIH is PHA. So yeah, I wonder if first we could show IH and K are collinear. So maybe it's worth drawing the circumcircle of ABC. Yeah.
Draw the parallel through H to BC.
Okay. So yeah, it's going to be tangent to that circle.
Let it intersect AB and AC.
All right.
Then circumcircle of AJM passes through that tangency point.
Okay.
Also just observations, nothing proved yet.
Okay. And yeah, the circle AJM is tangent to the circumcircle of ABC. Let's see if we can prove that. That seems like it shouldn't be. Are L, I, and J collinear? Looks like it, yeah. Let's just make sure that's true. Oh no, that's not true.
About proving that AJM is tangent to the circumcircle, it is obvious.
Yeah.
Because, yeah.
It's just homothety, yeah. So yeah, can we show KH and I are collinear? Wait, what were you saying? Were you saying something about the point K? I forgot.
I don't think I said anything about point K.
Okay. So BD equals CK. How do we use that? There's a lot going on in this diagram.
AI, EF, and JM concur.
AI, EF, and JM. Is FEJM cyclic?
Yes.
Okay, so really it's just the radical axis theorem, I think, right?
Well, it depends on how we define point I, but yes.
Oh, yeah. And then maybe if we connect L with that point, maybe L, N, and B are collinear. Just a guess. I don't know if that's true. I don't think so. Um, yeah, I'm not sure how to use that BD equals CK. Maybe I could draw the midpoint of BC. I don't know if that would help, but so we know that O is the midpoint. Let's call it something better.
Maybe we should consider the cross ratio BCDK.
Ah, okay.
And because we want to prove that K, H, and I are collinear, then at some point we should project through H.
Okay. Yeah, no, I think that's a good idea. So yeah, we want to show the cross ratio BDKC. Yeah, maybe we could try projecting on AN or EF. Maybe EF might be best.
But we really need to prove that AIDK is cyclic.
AIDK is cyclic.
Yeah, because if IHK were collinear, then KIA would be 90 degrees, which is KDA.
Ah, I see. Interesting. Okay, so we want to show that AI KD is cyclic. Yeah, maybe we could extend AN to meet BC.
We can prove that. I also did that in my solution that AI decay cyclic. So you just need to label the intersection of EF and BC.
EF and BC.
Yeah.
All right.
Let's call that point G.
Okay. We'll call it G.
Then we call the intersection of AN and BC.
Hold on one sec. AN and BC.
Yeah.
All right.
Let's call that point R. Oh, we already have R. Okay, let's call it Q.
Q.
So we have I can prove that Q is the midpoint of GD by using Menelaus.
Okay, so you want to show Q is the midpoint of GD?
Yeah, Q is the midpoint of GD by applying Menelaus to triangle GOD and the 3 points A and Q.
So usually whenever you use Menelaus, you could also use cross ratios. So like what if we took GQD? We want to show the cross ratio GQD infinity
that is trivial. Yeah, you're right. Because
sorry.
they are both equal to AHOD.
Okay, so you're projecting onto AD. So and then you get AHOD, and those are in harmonic conjugation. Okay, so yeah.
So Q is the midpoint of GD. So I'm gonna use the point K right now. So I have a claim that H is the orthocenter of AQK.
Okay.
So if we can prove that, then KH and I must be collinear, right?
Right, yes.
So notice that H is the orthocenter of ARG.
H is the orthocenter of ARG. Yeah, yes, that's true.
Yeah, and then we just work with the midpoints and thing to prove that H is the orthocenter of AQK.
Okay, because
okay, I'll just present it. Okay, we have GK triangle GDH is similar to ADR.
GDH is similar to ADR.
Yeah, and we have Q is the midpoint of DG, and R is the midpoint of DK. So we will also have that HDQ is similar to KDA.
Yeah, I actually think I saw it another way. So basically, like we know the reflection of the orthocenter over the side lies on the circumcircle, right? So yeah, I kind of thought of a different way to do it, but basically, like let H prime be the reflection of H over BC. So basically, you said that like we know that so we know that this is cyclic, right? Because the reflection, because H is the orthocenter of AGR. So GD times DR. So GD is twice QD, and also DR is half of DK. So that would mean that AQ H prime K is cyclic with orthocenter H. Does that make sense? That's kind of how I thought of it.
Yeah, that is cool too.
But I think your way is probably the same. Gets you to this. Your way is probably the same idea.
Yeah, it is the same because I just see the triangle are similar, so I approach that way.
Okay, so that means that H is the orthocenter of AQK, And so therefore, KH and I are collinear. Okay. And then we have to prove, so yeah, I like that idea. And then we have to prove that the circumcircle of ATL, where is L? I forgot. Oh, L is right there. We have to show that, so omega is supposed to pass through H and T. We have to show that this circumcircle of IPH is tangent to AH. So it looks like IPHN is cyclic.
It is.
It is, yeah. So, okay, so we have angle NPH is NIH is 90. And so, yeah, that shows that it's cyclic and it's tangent to AH. And I think that solves the whole problem, right?
Wait, do we know that LATI is cyclic?
Do we know that ATIL is cyclic?
Yeah, and we need to prove that that circle also is tangent to.
Yeah, we had to show their tangent. That's true. So yeah, there still is one more step.
But do we know that it exists, that it is cyclic?
Let's see. So I thought we defined point I to be the inner, so like I thought we defined point I to be the intersection of ATL and this circle. So that's kind of how we defined it. And then you see what I mean?
Yeah, so with that definition, we can prove things, right?
Yeah.
Okay, then. So we need only to prove that it is tangent.
I think we define I as the intersection of AH and omega, not ATL. Because I think I used the fact that I lies on omega to prove that Q is the midpoint.
Oh, so, okay. So omega is this circle right here?
Omega is the circle with diameter HN.
This?
No, I mean the omega in the problem. In the
I thought
I can just recheck if I used any fact about that.
okay. But yeah, I don't think we did. I think we can define I this way. And yeah, I don't think we need this circle right here. It's an interesting fact. Well, yeah, but yeah, I think it's enough to define I this way. And then it's easy to show that NIPH is cyclic and tangent to AH. So then we know that this circle is omega. And then we want to show that these are tangent. So yeah, how do we do that? Let's see.
But we need to prove that N exists if we define I the other way.
But I think it would, is it by the radical axis theorem? Because we have AI, let's see, sorry.
For that, we need to prove that AIJM is cyclic.
Oh, okay. So that's where we use that fact. Okay. So we have to show that AIJM is cyclic. Yeah, you're right.
Wait, so can you just explain what we did, like how we define the points and what are we going to do next?
Yeah, so I said define I to be the intersection of the circle ATL and this circle. Then we can define points G and Q, and by everything you said, then we can show that H is the orthocenter of AQK.
So we have one problem. So we didn't have I lies on omega, right? So we didn't have NH is parallel to BC. Because if NH is parallel to BC, then I must lie on omega.
Yeah, so you're right. So we have to prove. So you're right. If we can show AIJM is cyclic, then we can show that point N exists, and then it's not hard to show that. So yeah, we want to show AIJM is cyclic, and then we would be able to do that. So yeah,
I think it's a little hard because we haven't find the way to use circumcircle AIL.
Yeah.
Because originally in my solution, I defined I to lie on omega first, and then I proved that ALIT is cyclic later. But you can just use your way to if you want to.
I think we might be able to use the power ratio lemma to show that AIJM is cyclic, because basically the ratio of the powers, it would be JH squared versus JT times JA, and MH squared versus MA times ML. Yeah, so we want to show that JH squared over JT times JA is MH squared over MA times ML. And let's see. But wait, so JH squared over JF times JA. But we know that JF times JA equals JA. JT times JA.
If we want to use the power ratio lemma, then we need to prove that JF over JT is equal to ME over ML.
Interesting. And I wonder if we could do that with cross ratios somehow. So JF over JT equals ME over ML.
Yes.
Because yeah, that's like a pretty simple configuration, right? Because you just you take the perpendicular from H to EF and it intersects at T and L, and these are the perpendiculars from H to the sides. Interesting. Two. So maybe we could let HP, like what if we, I think this might make it easier. Sorry, give me just a moment. What if we let this meet side BC at point? And then we could use projected geometry a little bit. Let me check the chat. Okay. Yeah, it's tricky. So we have yeah, we could use A in it. So if we take F, T, J, and A and we project it onto this, we get C, S, D, infinity. So basically we want to show C. Yeah, I'm not sure how much that would help. Or like, what if we did FTJB and we projected it through H? So CS infinity B. And then if we did M, A, and L and we projected it through H. We get B, D, S. Okay, so basically, like, let me write out some of the cross ratios. So I like F, T, and J. I just don't know whether I want to use A or B. Yeah, it starts to get a little complicated. Let me see if there's another way to show that AIJM is cyclic. Maybe we're making it too hard. DC infinity and S. Yeah, I'm trying to, so we want to find JF over JA. I could try drawing the parallel through H to AB and letting it intersect BC. I mean, that doesn't seem like it should be so bad. So like, this is a parallel through H to AB. So then I would have the cross ratio CSU infinity. So I want to show that CS over SU is equal to
I think it's a little late, so if you don't mind, I can just present my solution.
okay, yeah, sure.
So I'm not defining I as the intersection of circumcircle with diameter AH and
Okay,
ALI, but I'm defining I to be the intersection of omega and AH.
okay.
So can you just temporarily hide the circle AIL?
Yeah,
Because I'm going to prove that is cyclic later.
okay. So
Okay,
you
so
define I as the intersection of omega with
circumcircle AH, the circumcircle AHE.
oh, okay. So okay.
So based on what I said, we can prove that H is the orthocenter of AQK.
Okay.
And then thus I, H, and K are collinear.
All right.
And also NH is parallel to BC.
Okay. So you define, let's start from the beginning. So
So we define I, you can just write it down.
I'll just do it like this. A FIE intersect omega. Like that.
And we define N to be the intersection of the line through H parallel to BC with AI.
Okay. All right. And then I guess, and then we show that J.
I mean, N is the intersection of EF and the line parallel to A.
The intersection of EF. Okay.
Yeah.
And then we try to show it lies on AI.
Wait.
Okay, so then we could use the radical axis theorem, I'm guessing, right, to show. Well, but yeah, we don't know that it's cyclic. Okay, so what's the next step?
I think we should call I be the let I be the altitude, feed of altitude from H onto AN.
Okay, so let I be, okay, so first define N, it basically is what you're saying. And then let I be the altitude from H to AN. So right. And then AIFHE is cyclic, right?
So we define point Q first. Oh, wait,
Okay.
AIFHE, yeah.
All right. So point Q
is intersection of AI and BC.
and BC. Okay. So let Q be the intersection of AI and BC.
Then we call G the intersection of EF and BC.
Okay.
And then we will prove that Q is the midpoint of GD, and then we apply the what you said before to prove that AQK is H is the orthocenter of AQK.
So I think we might be missing one step. So how did we know? Okay, so Q is the intersection of AI and BC. Okay, I think you're right. So okay, so we have GD Q infinity is equal to OA. So ODA H it's around harmonic conjugation. So Q is the midpoint of GD. And then, so we know H is the orthocenter of AGR. So I'll say let R be the midpoint of BC. So H is the orthocenter of AGR. That's kind of well known. I'll just say it's well known for now. So basically, I'll say let H prime be the intersection of those two circles. So let AGR and ABC meet at H prime. And then basically we have we have AD times DH prime is GD times DR. Which is 2QD times dk over 2, which is QD times dk. So So that means that AQH prime K is cyclic with orthocenter H. Since the reflection of the orthocenter lies on the circumcircle. All right. So then we have that fact. Okay. So, yeah.
So we can prove that AIJM is cyclic now.
So now we can show that then we know that H, I, and K are collinear, right? So we have angle KIA equals 90 implies I, H, and K are collinear. And then now we have to show that that's cyclic, right? So AI, okay, so the next step is we have to show that ATLI is cyclic, right?
So I'm proving it by using radical axis and stuff. Like we need to prove that. Can you draw the line through T and perpendicular to AB?
Yeah. Through T perpendicular to AB.
Yeah, and can to AB, not through AH.
Oh, sorry. There we go.
And can you draw the line HI?
HI, yeah. You bet.
And the line through A perpendicular to AH. I will prove them they are concurrent.
Okay.
Michael, I think I solved the first problem. That we.
Oh, really?
Yeah. But we don't have time.
Yeah. Put it on the Discord. I'm curious. I want to know the solution.
Okay. It is interesting because I did something. I don't remember exactly what I did, but it simplified the picture a lot.
Okay.
And I just needed to prove that 3 tangents to 3 circles concurred.
Interesting.
And I think I've done that with an angle chase.
All right. Yeah, I'm curious. Put it on the Discord, and yeah, we'll take a look at it after the session.
Yeah, I will write it up. First, I will see it if it is good, if it has an error or something, but I will write it.
All right, sounds good. Okay, so you're going to show that these 3 lines are concurrent, right?
Yeah, then if we can do that, then we can prove that UL is perpendicular to AC.
Okay, then we could show that what's perpendicular to AC?
UL.
UL, okay.
And then we can show that UITA and L are cyclic because they share the same diameter.
Ah, I see. Okay, yeah. So
I'm doing this by using the radical axis theorem.
Okay.
So can you call it the intersection of TU and AH?
TU and AH?
Yeah.
Okay. What was the other line I had here? Was it, I forgot.
No, no, it's not MU. Like it's just the line through T perpendicular to AB. And it meets AH at a point.
Okay.
V, okay. So if we can prove that ITVH is cyclic, then we just apply the radical axis theorem through with circle with diameter AH and that circle and omega.
Okay, so first we proved that ITVH is cyclic. So I'm just gonna write it here, up here. So first prove IVTH is cyclic. And then once we know that, then we can use the radical axis theorem to show that
the three line concur.
Then use the radical axis theorem to show IHTV and the parallel through A to BC, I'll say. And then show that LUITA is cyclic with diameter AU. Is cyclic with diameter AU. So I'll say concur at a point U. Oops, sorry. So basically this is, and then from there, it's not hard to show those circles are tangent, right? Because if this is the right angle, yeah. Okay, so I'm just gonna write out, yeah, then it is easy to show the two circles are tangent by a homothety. All right, I think this is good enough. So yeah, I'll let the viewers sort of fill in the details, but I think this shows how to do it good enough. So yeah, I like this solution. This is a good one. All right. So yeah, thanks everyone for participating. And thanks for the people watching on YouTube. Thanks for watching. So if you want to join future sessions, feel free to email me at mgreenb801@gmail.com. It's in the description of the video. And we meet at 8 a.m. US Central Time every Sunday. So thanks again and have a great day.